After basic character, the next reaction is alkylation. Alkylation, which is same as ammonolysis. Here we are learning the reactions of amine. So we are starting from amine, plus alkylation. For that we are plus alkylation, plus acylation. We will take this alkylation CH3. So here we get in CH3 NH CH3 plus HCl. We are getting a secondary amine. And again, this on CH3C will be getting tertiary, then finally quaternary ammonium salt. Alkylation we have already seen. Next is acylation. In acylation, we use acyl chloride CH3 COCl. I'm writing down amine, that is CH3 NH2 plus CH3C double bond OCl in a different fashion. Here, this H, this is a pair of electrons. This bond is polarized, that is C plus, this will be attacking the C plus, and we will be getting CH3 NH plus H, and this bond C O minus and CH3. Now what happens? This pair of electron is taken to cancel, this H will go as H plus, and this pair of electron will end up here, so Cl will go as Cl minus. So you will be getting CH3 NH C double bond to CH3. HCl has gone. HCl has gone. Here, this is the pairing side. So this is ethanamide, N-methyl ethanamide. This is N-methyl ethanamide. So C double bond O is connected to the other end, CH3 end. So this is N. N-methyl ethanamide. Here, ethan, this is C2C, that is if it is NH2, it is ethanamide, and C3 is connected to this N, so it is N-methyl ethanamide. So acylation. Similarly, you can do benzoylation. For benzoylation, instead of CH3, you will be writing C6H5. C6H5. So here, this C6H5 will be coming here, C6H5. So it is actually benzamide. This is C6H5. Then it is benzamide. C6H5CONH2, benzamide. So that side is the enzyme. So N-methyl benzamide. That is benzoylation. If it is C6H5COCl, it is benzoyl chloride. So we say benzoylation. Next is acetylation. Acetylation is a reaction with acetic anhydride. Acetic anhydride. Reaction is similar. Alkylation, acetylation, then acylation, acetylation, and benzoylation. I'm taking one CH3, COOC, double bond O, CH3. So here what happens, this H and this much portion, instead of that Cl, now the connection is this much. So this acetic acid will be going and the CH3Cu will be getting connected as in the case of acylation. Instead of the side product HCl, here the product is CH3COOH. The product is similar, that is CH3NH. NHC double bond O CH3. This is ethanamide and methyl ethanamide. Similar to that, acylation. So acylation, acetylation, benzoylation, the reaction procedure is this. That is the third reaction. Fourth reaction of amine is carbylamine reaction. First is chemical property, that is basic character. It reacts with acid. It reacts with acid. We saw in gaseous phase what is the order, in liquid phase or aqueous phase what is the order. Then we learned about alkylation. Then acylation in that category, acylation, acetylation, and benzoylation. Next is carbylamine reaction. Carbylamine reaction. It is also called isocyanide. Isocyanide test. Isocyanide is a test or the reaction given only by primary amines, aliphatic or aromatic primary amines. That is AR or RNH2 in presence of chloroform and alkali. Chloroform, CH3, chloroform and alkali gives RNC plus 3KCl plus 3H2. So here 3. This is isocyanide. Isocyanide. It has got a foul smell. Foul smell. It is poisonous gas, isocyanide. If you are getting this foul smell, then you have taken what a primary and secondary and tertiary will not give. Secondary and tertiary will not give this test. So this test can be used as a distinguishing test between primary and the other. Carbylamine reaction. Remember, all these are 3 CHCl, 3 chloroform, and 3 KOH, 3 KCl, 3 H2. Carbylamine reaction. Whether it is aride, then also we get such 5 NC. So that is carbylamine reaction. And the fifth reaction is reaction with the nitrous acid. Nitrous acid, that is HNO2. HNO2, how can we get HNO2? HNO2 is made by mixing NaNO2 and considered HCl. The diazotization reaction, what we have learned previously in haloalkanes and haloarynes, the same thing. That is, we are starting with aniline. I'm writing this aniline first because this is familiar to you. That is the concentrated HCl, NaNO2, and NaNO2 below 5 degrees Celsius, that is 0 degrees Celsius, or 473 Kelvin, different names. So here you will be getting benzene disodium chloride, that is N2Cl. Benzene disodium chloride is somewhat stable, not very stable. We know that warming with water, you will be getting what? Phenol. In the similar way, I am writing alkyl disodium chloride. Alkyl disodium chloride. Alkyl disodium chloride, that is CH3NH2. Alkyl disodium chloride, in the same similar manner, that is concentrated HCl. I can write HNO2. You will see HNO2 below 5 degrees Celsius. Instead of this, HNO2 with the nitrous acid. Nitrous acid is the output of this mixture. So you will be getting what? CH3N2Cl. This is ADC. Here we learned ADC. That is ADC, alkyl disodium chloride. You don't have to do anything. It itself decomposes, that means it is highly unstable. It decomposes to form CH3OH. Here you are warming with water, that it is highly unstable, decomposes to form alcohol, aliphatic alcohol. That is a reaction with nitrous acid. And here N2 is the side product. N2 and HCl are the side product. So here primary amines will produce this N2 gas. Primary amines will be producing this N2 primary amines will be producing this N2 gas. You will see liberation of nitrogen gas. You'll be, if you are seeing a liberation of a gas, means that is nitrogen gas only. So here secondary and tertiary will not be answering this test. So this is again a test to distinguish between primary from secondary and tertiary. The previous one was carbamide reaction. Next is reaction with benzene sulfonyl chloride. Benzene sulfonyl chloride is known as Ginsberg reagent. Ginsberg reagent. Reaction with the Ginsberg reagent. So this is number 6, Ginsberg reagent. Benzene sulfonyl chloride, that is this H5, SO2Cl, SOS double bond OCl. This is benzene sulfonyl chloride. Now see that. Benzene sulfonyl chloride. That is S double bond O double bond OC. Benzene sulfonyl chloride. We are going to treat this with primary, secondary, and tertiary separately. With the primary, that is plus CH3NH2, CH3NH2 or C6H5NH2. H from here and Cl from here will go as HCl and this will be connected here. This sulfur, due to the presence of 2 electron withdrawing oxygen groups, it is highly positive. So this pair of electrons will be attacking that. You will be getting what? Nitrogen will be attacking there and what HCl will be good. You are getting a sulfonamide, benzene sulfonamide, N-methyl benzene sulfonamide. The speciality of that compound is that there is one hydrogen concentrate on that hydrogen. The entire property is based on that hydrogen. Due to the high electron withdrawing effect of this double bond O, this H will be highly acidic, or that NH, that bottom pair of electrons will be pulled by this side, S double bond O sides very easily. So H can be liberated as H plus, so that hydrogen is highly acidic. If you treat this with an alkali, then it will be soluble in alcohol. It will be soluble in alcohol. So what you have to do is take benzene sulfonyl chloride. 1 degree, 2 degree or 3 degree, I mean what you want to test you that. If it is 1 degree, you put that 1 degree. After putting this, you have to put alkali. So first step is putting what you have got 3 test tubes having 1 degree, 2 degree, 2 degree, 3 degree. We don't know which is having which. To all you are putting benzene sulfonyl chloride, and followed by alkali. If you see everything soluble, only one phase. If you see everything soluble, that is 1 degree. If you see everything soluble, suppose if you see everything soluble, that will be 1 degree. After adding alkali, if it is insoluble, means what all things you added? One compound is there, so that you added benzene sulfonyl chloride and you added alkali. After adding all the 3, if you are getting only, if you are getting 2 phases, two layers, that means you are getting a compound after adding alkali, if you find it is insoluble, then it is secondary. Then it is secondary. Why? Because in secondary there is the CH3. After the removal of this HCl, here there is no H presence. Instead there it is CH3. So there is no acidic hydrogen. It cannot act as an acid. So after adding alkali, it will not be soluble. So if it is not soluble means you will be getting, after adding all these three, this is 1, 2, then alkali. This is produced on its own. You don't have to add. What it is you are doing, you are adding this plus the substance under investigation and followed by alkali. If it is insoluble, then it is secondary. Then it is secondary. So when you add this and this, you will be getting only one phase, only one compound. Now, if it is tertiary, what would have been happening? If it is tertiary, on addition of this benzene sulfonyl chloride, you will not get that compound. Whatever things you added, it will be as 2 layers here. So tertiary will not be reacting with the benzene sulfonyl chloride. So tertiary will not react. How can you distinguish between primary, secondary and tertiary? Using Campbell-Lewin reaction, you could make out which is primary. You can distinguish primary from secondary and tertiary, but you cannot distinguish between secondary and tertiary. Even with the nitrous acid, the liberation of nitrogen shows whether it is primary, but you cannot make out whether it is secondary, or you cannot distinguish between secondary and tertiary. You can say, okay, this is primary. But by this method, by Ginsberg reagent, that is benzene sulfonyl chloride, you can make out whether it is primary, secondary or tertiary. You can distinguish. What are things? The substance to be investigated, you take in a test tube, add benzene sulfonyl chloride. After that, you add alkali. You see everything is insoluble. Sorry, everything is soluble. If it is soluble, it is primary. After adding all the three, if it is insoluble, then it is secondary. After adding first two, that is the amine under investigation, benzene sulfonyl chloride. If you see 2 layers, that means they do not react with each other. So tertiary will not react. Tertiary will not react. So that is tertiary. So by using the Ginsberg reagent, you can distinguish between primary, secondary, and tertiary. While naming, you should take care that this side is the parent. This is benzene sulfonamide NH. You are having NH, that is substituted with N-methyl here, NN dimethyl. NN dimethyl benzene sulfonamide. NN dimethyl benzene sulfonamide. So that is how, using Ginsberg reagent or benzene sulfonyl chloride, you can distinguish between primary, secondary, and tertiary. Okay, next is electrophilic substitution of electrophilic substitution. That is the 7th reaction. First was basic character, second alkylation. In that alkylation, okay, second is alkylation, then acylation, acetylation, benzylation. Next is carbylamine reaction, and the 5th one is reaction with nitric acid. Then 6th is with benzene sulfonyl chloride. 7th one is electrophilic substitution. And electrophilic substitution reaction, when we say electrophilic substitution reaction, it will be C6H5 NH2. There should be a benzene for electrophilic substitution reaction. An electrophile will be coming and attacking. Of course, this is similar to phenol. It is highly activating this pair of electron or nitrogen will be coming to the single bond to make it as a double bond and getting 5 structures. At ortho position and para position, you will be having the negative charge. At ortho and para positions, you will be having the negative charge. Similar to phenol, you know that phenol on reaction with aqueous Br2. you were getting that is 2,4,6,5 bromophenol, which precipitated as a white precipitate, which deposited as a white precipitate. That is how do you distinguish phenol from other similar compounds, similar molecular mass compounds, similar molecular mass other functional groups. Similarly, here also with aqueous Br2, that is H2O Br2, or you can write aqueous Br2, you will be getting 2,4,6,5 bromo aniline. 2,4,6,5 bromo aniline. Again, this is again a white precipitate only. This is a white precipitate. This is aniline. NH2. NH2. 2,4,6,5 bromo aniline is white precipitate, similar to our 2,4,6,5 bromo phenol. So you cannot distinguish phenol and aniline by this aqueous Br2 because both will be giving white precipitate. While this 2,4,6,5 bromo is coming because this is amino group is highly activating like phenol, that pair of electron will be entering into the resonance. So this NH2 group is highly activating. How can you show that this NH2 group is highly activating? For that you have to show these 5 resonance structures, and you say that this NH2 group is activating this benzene ring, showing negative charges at ortho and para position in those 5 resonance structures. To get only mono substituted product, that means mono bromo instead of this 2,4,6. Suppose you want the most stable para bromo aniline. If you want mono substituted, then this activating effect of NH2 should be controlled. Means this pair of electrons should not be entering or should not be entering much to the benzene ring, so that activating effect of that NH2 group can be reduced. See, this is aniline. Why it is highly activated? Because that pair of electrons will be entering into the resonance. Right? Ortho and para position will be highly negative. So, what you have to do? You have to tie it up. You have to catch hold of that pair of it. The pair of electrons should not enter here. For that, the pair of electrons should be taken to other part by doing some fitting, so that this pair of electron can be taken to some other side. For that, what we are doing acetylation. Means you are introducing a C double bond O to this nitrogen. C double bond O, if it is fitted to that nitrogen, then one pair of electron can be pulled to that side, as in the case of semi-carbazide, that pair of electrons from nitrogen is taken to that C double bond O. So what you are doing by acetylating this thing, you are making that H C double bond O shift. By acetylation, you can fit that acetylate this. So what happens now? This pair of electrons will be entering into the resonance, so that pair of electron going to some other part. So that pair of electron is not available to enter to this. So the activating effect of this amino group is reduced. Now you brominate. Brominate in less polar solvents, not with water. Water again there is a slight problem. So weakly ionizing water is highly polar. Weakly ionizing acetic acid, that is ethanoic acid. So Br2 ethanoic acid. Br2 ethanoic acid. Ethanoic acid. Br2 ethanoic acid. Don't give a polar solvent there. Br2H2O, aqueous Br2, like don't give such highly polar solvent. Br2 ethanoic acid is weakly ionizing acetic acid is weakly dissociated. So here, what happens? You will be getting that NHCOCH2 and para-bromine. We'll be getting para-bromine. To get back aniline, acidified H+. On acidification, you will be getting the final product that is the neon layer, NH2, and here neon. This is how we are getting para-bromo aniline. Para-bromo aniline. So what all means why did we fit this thing? To reduce the activating effect of this NH2, that means this pair of electron should not enter to this instant, it is taken to some other portion. For that we are creating one C double bond to you acylate it, you acetylate it. So this pair of electron can be taken to the other side. After that you do bromation, and bromination also not with aqueous. With ethanoic acid, you do VR to ethanoic acid. In the case of ether also, we did VR to ethanoic acid because in ether also that OCH3 group was highly activating. So VR to ethanoic acid, you can get what this. Then after that, if you brom, you can get this para-brom. To get back again NH2, that is this NH2, you can do acidification. On acidification, you will be getting para-brom. That is the electrophilic substitution. If it is aqueous Br2, all the 2,4,6 will be brominated. Next is what? Nitration. Nitration, of course, this NH2. There is a big problem in nitration. What you are doing for nitration? You are putting concentrated H2SO4 and concentrated HNO3. This is the nitrogen mixture you are adding to nitrate this aniline. Concentrated H2SO4 and concentrated HNO3. Highly acidic medium. This is a base. You are going to nitrate this. This is a base. Phenol, if it was phenol was acidic. But this is a base. In strongly acidic medium, what will happen? This pair of electron will be utilized to make a bond with H+. In strongly acidic medium, this will be, instead of going for nitration, first this will form what NH3+. When it is NH3+, it is highly reactivating. There is no electron on nitrogen. Here there was a pair of electron on nitrogen. There it was plus. There it was plus. So it is highly reactivating. So highly reactivating means the product will be meta product. Deactivating means product will be meta. So significant amount of meta is also produced. Here meta is produced. 57% meta is produced. Of course, looking at that aniline, first we are going to write para. This is no problem, para. Of course, para is also produced. Para is produced 51%. And ortho is produced very less %. Ortho is produced only here. Ortho is produced very less and significant amount of meta. Significant amount of meta is also produced. 2% is 47%. So significant amount of meta is produced. Para is there. Aniline. But what happens? One more thing is happening here. In strongly acidic medium, aniline changes to anilinium ion, which is meta-dialectic. So you are getting meta product also. Significant amount of meta product is also obtained. 47% of meta is obtained. Thank you.